Hey, what's up, guys? This is Chung here again. So this time, let's take a look at 1697, checking the existence of edge length limited path. So, I mean, this is another graph problem. I think it's quite interesting. And you're given like a graph of n nodes and in the form of a edge list, which is a u, v, and distance between those two nodes. And you're also given like an array of queries. So the queries is also like a U and a V, or you can call it P and Q, right? So U and V, and then there's the limits. So your task is to determine for each of the queries if there's a path between this P and J, sorry, the P and Q, such that there exists a path that uh, the path on each I mean the distance on each of the edge is strictly less than the limit. And note that there may be multiple edges between two nodes. Right, so that's the basically the description. And here's one examples here. So we have the three nodes here, 0, 1, and 2. And we also have four edges here. So 4, 8, and from 1 to 0, between 1 and 0, there are two edges. So one edge has distance 2, and the other one has 16. That's why we have two values here. And then we have two queries. So the first one is from 0 to 1. So it's asking us to check. So from 0 to 1, the path, right? The path from 0 to 1, if there exists a path from 0 to 1, I mean each edge on that path is the distance is smaller than 2. And the answer is false because the smallest we can get the smallest path from 0 to 1 is 2. 2 is not strictly smaller than 2. So that's why we have false here. And then the second one is the from 0 to 2. From 0 to 2, if there's a path whose each edge is smaller than 5. And the answer for this one is yes, because we can have 2 and 4. That so here's a path. Okay. And yeah, so that's the description. And here's another examples here, right? And then the constraints. So the constraint is what? Is the 10 to the power of 5. The other one is 10 to the power of 5 as well. And here there might be multiple edges between two nodes. So that's the constraints. Um, so the brute force way to solve this problem is, for each of the queries, right? So for each of the queries, we'll try to find the shortest path between this P and between this P and the Q. And while and basically it's just like a Dijkstro problem solution. We use Dijkstro to find a path that can give us the minimum the minimum distance on each of the edge. And if that one is smaller than the current limits, then we know, okay, so we will return true in this case for this query. But the problem for that is that since we have a pretty big constraints here, so for it to loop through each of the queries, we need a O(n) time, O(n) time. And for the Dijkstro, right? So the Dijkstro's complexity is another n of log e if I'm not mistaken. So where n is the number of nodes and e is the number of edge. So in total, we have O of n square of log n, I think. Yeah, since the edge is also can be up to 10 to the power of 5, right? So, and this will TLE. And that's why this one is a hard problem, right? And we have to find another solution to solve this problem. Mm, a common solution for a graph problem, if we cannot solve it in a regular way, is a union find. Because the union find, so the union and find, the time complexity for that, after the path compression and some rankings, we can consider both the union and find to be O1 time complexity, and we just need to find the relations between the union find uh, characteristics and the queries and the answer for each query. If you watch this, if you read this thing more several times, you might be able to find that, actually, so when will we return true, right? And when will we return false? If we are if we sort the queries by the limits, okay, and let's say we have some queries here. We have queries uh, from P1 to Q1, right? And the limit is 2. And then we have another one that's P2 equals to Q2, and the limit is 5, something like this, right? And then P3, Q3, and maybe 8. So for 2 here, right? I mean, how can we know if this P1, Q1, 2 will return true? So it will return true if, like I said, if there are like some path that can connect. Oh, sorry, if there are some edges that can connect this P1 and P2, and whose distance, right? The distance is no bigger than 2. It's actually small. It's strictly smaller than 2, right? And same thing for this P2 and P2 and Q2. So we return true for this one if there are some edges that can connect the P2 and the Q2, right? Whose like the distance is smaller than 5. So if you can find this, if you can make these observations, now I think it's more clear that we just for each of the queries here, we just need to try to find some edges that whose distance is smaller than the current limits, and we'll try to connect these two nodes together. And that's a perfect candidate by using the union find. And now I think the solution becomes much clearer. So we sort the queries by the limits from smallest to the biggest, so that we can build the graphs bottom up. And then we also sort the edges list from the smallest distance to the biggest. And for each of the queries, and since we need to we also need to maintain the index for each of the queries. That's why uh, even though we're sorting by this one, but we're still going to maintain the original index, so that we can use the index to populate the final answer array. So basically, for each of the queries here, from the smallest to biggest, we use this one as a parameters, and we use it to find the uh, the the edges whose distance is smaller than this one, and then we will try to union those edges. And after that, we simply check if this P1 and Q1 is connected. if it is, then we know, okay, so there has to be a path that can satisfy this condition, and then we return true. Otherwise, we return false, right? And since we are like sorting this queries from smallest to biggest, so whenever we have union sum of the edges here, we don't have to go back to do it because it does we don't really care, right? Because we can use as many edges as we want as long as they are smaller than the current limits. So that's why we can just try to union everything that's smaller than this one, and we can just keep adding the edges, and then yeah, and then there you go. So we for each of the one we just use the same logic to check, and then we should get our final answer. Cool. So I will start the implementations here. I think first I'm going to try to create templates for the union find, right? So for those who still don't know the union find, I recommend you to find some other videos that can give you a better explanations about the union find. So here I'm only going to do the implementations. So for union find, we need two functions methods. The first one is the find. So the find is find the root, right? So find the root for the current group. So the way I'm doing this, I'm using a path compression, right? So here I'm using recursive call for this current one, and then we do a find of the parents x, right? And in the end, I return the parents. So that's that. Because at the beginning, every node has itself as served as the as a parent, and that's why whenever the parent is not the number itself, and then we know, okay, so this current number has a different has another root. That's why we just keep looking up. While looking up, we also compress doing the path compression. So that's the find, and then we have a union, right? So the union is this x and y, and we just do a R1 equals to find x, right? And then R2 equals to find of y. And then if R1 is not does not equal to R2, and then we do the union. And here I'm not using the rankings. Here I'm just using the sorry. I'm just always assign this R1, the parents of R1 to us, parents of R2 to R1. Okay, so that's the templates of the union find, and after that, let's just try to sort this two list. So the first one is the edge, right? So for the edge, we want to sort by the distance, which is we need to use a lambda function, right? So we have a x dot x 2, right? So that's the third element, and then we also need to sort the queries by the limits while also maintaining the index. That's why I'm going to create a new list of queries. And so the first one is the limits, and then we have a u, we have a v, and then we have an index. And I'm going to do a like loop here for u and v and l, right, in enumerate of the queries. Queries. So I'm just using a short versions of the for loop here. So I'm just uh, enumerate the queries, including the index itself, and I just create a new uh, tuple or set, a tuple, right, for each of the query itself, so that I can just easily sort by the limits. Now I can just do a sort. And I don't even need to specify the lambda functions because by default it'll be sorted by the first element, which is the limit. That's why I put the limits at the first one. All right, cool. So that's that. And now we can just now we need the answer, right? So I mean the answer at the beginning, everything is false, right? And the length is the length of the course. Oh, and that's why we need the m here. So I'm going to use, since we already have n here, I'm using m. M is the length of the course, right? Yeah. So that's that. And then we have a for queries. So I'm going to have like the limits. So I would also spell it out. So the query limit, right? And then we have a u, we have a v, and we have a I, right? In the queue. That's that. And so yeah, and in the end, right? Once we have our answers, we just need to do a answer dot I equals to the something, right? Either true or false in the end. And then later on, in the end, we simply return the answer. So the way we're doing this is, like I said, we have to, with the current queue limits, we'll find the valid edges that to, we can use to do the union. And the way I'm finding it is I'm going to introduce another like edge index of equals to 0 at the beginning, right? And then while the edge index is smaller than the size. Okay, then I need another one. I need another length, which is I guess I'll just call it an edge size, maybe. That's the length of the edge list. So while this one is smaller than this, and edge list of the edge index and number 2, right, is smaller than the queue limit. Now, since the edge list has 3 elements and the index 2 is the distance we're looking for, right? And since the edge list is already sorted by this one, that's why I can just loop through from the current index. And if the current one is smaller, the current distance is smaller than the limits, I can just do the union, right? So the union is I'll union the edge list of this, which is 0 and 1, right? So the 0 is the u and the 1 is the v. So I just union those two. And then after that, I just increase the index by 1. Since this edge has already been unioned, so we don't have to use it anymore. That's why we can just keep moving the edge index forward. Cool. So, and once this while loop is finished, we have used all the the valid edges we can use to try to connect the current uh, queries, right? And then we can simply check use assign these answers with the find of u equals to the find of v. So what this one does is basically this is the way we're checking if the u and v has been connected, or in another word, if the u and v belongs to the same group, right? So find u and find v give us the same group here, right? And then we can use we can just return true because we know, okay, so we have already find a path, otherwise false. Yep, I believe that's it. So let me run the code. Oops, sorry, invalid syntax. Oh, it should be a colon, not semicolon. Queries. Oh, yeah. Queries. Queries. Okay. And all right, accept it. Okay, so it's it's successful. yeah, so that's it. And so for the time complexity, right? So, like I said, so the union and the find, we're treating it like a O1 here. So we can just ignore these two parts. And so the most significant complexity is this two sortings, which is are both n log n, right? Because both the edges and the queries can be up to n length. That's why and then here we have so we have n log n here. Here's like just a O of n, and but here, since even though we have a while loop here, but we're only going to use the each edge once. That's why so here we can also consider like O1, right? And then the find and union, they are also O1. So in total, I mean it's a it's an n log n solution for this. Yeah. Yeah, I guess that's it for this one. I think this one is it's a very interesting union find solutions. And so the observation you have to be able to make is how can you relate, or how can you connect the the the, the answer for each queries with some union find algorithm. And in this case, it just happens to be I mean, you just have to uh, write it down, or and then try to analyze. So what does the true mean for each of the queries? And so for this one, it means that, and with this kind of limits, can we find some edges that can connect P and J together? So that's the meaning of true for the queries. And if you after that, I think it shouldn't be that too hard to find a sorting and also this while this like index thing. So you can solve this problem into n log n time complexity. And yeah, I think that's it for today, I guess. And thank you so much for you guys to watch my video, and stay tuned. See you guys soon. Bye bye.